Hello, and welcome to this Chemistry World webinar, which is all about harnessing the power of electricity to make organic compounds. I'm Philip Broadwith, I'm Chemistry World's business editor. Just a few housekeeping things before we get started. For those of you not familiar with the GoToWebinar platform, you should see a panel on the right, by default is on the right-hand side of your screen, but your display may change. GoToWebinar is an interactive platform. That's part of the reason why we use it. The whole point of doing these webinars is that we want you to be able to interact with our experts and ask questions and get the most out of coming to these sessions. So please do make use of that facility. Ask your questions. You can ask questions at any point during the webinar using the questions box, which should be towards the bottom of that panel. Please don't wait till the end. It's much easier for us if we can see your questions early on rather than them all coming in together at once, and you're more likely to get your question answered if you ask it during the course of the webinar. If you do miss any part of the presentation, don't worry. If you have problems with your connection or the sound goes out or whatever, it shouldn't be a problem. You will get a full recording of the webinar in your email in a couple of days' time. At the same and to say thank you to everyone for coming, you will also get a certificate of attendance in the same email. So today's webinar is about using electrochemistry, electrosynthesis to make organic molecules using batch type electrochemical reactors. Electrochemistry opens up a whole load of interesting new modes of reactivity, but it does require different equipment that may not be familiar with to everyone in standard labs. So the point of this webinar, one of them, is to, by the end, you should be able to understand how to get the best out of electrochemical batch reactors and how to handle some of the equipment and properly. We have worked with Merck KGaA from Darmstadt in Germany to bring you this webinar. We think that it's information that you will be interested in, and they have access to some highly specialized experts in this field, including our speaker today, who is Siegfried Waldvogel. He is a professor at Johannes Gutenberg University in Mainz in Germany, but he's also the founder and senior research scientist at a startup company called Easy Labs, which develops electrosynthesis technology for a whole variety of different applications. So Siggy, I can see you on the camera. Can you see and hear me okay? Everything looks good. Good to see you. So I think we are good to go. I'm going to hand over to you, and please take it away with your presentation.
Okay, thanks Philip for the nice words of introduction, and I'm really pleased to be here and show you a little bit how we do the electrosynthesis. And it's really not very difficult if you have the right equipment to harness the power of electricity and get prep amount of compounds by electrosynthesis. Why should we focus on that? And as you know, in many countries, especially in Germany, coal firing and gas firing will be switched off pretty soon. The nuclear power plants are mostly switched off. We will rely more and more on regenerative power sources. This will feed into the grid, but the supply is not usually the same what is in the demand. Now you could say, okay, then we just have a big battery, but big batteries at that size are not feasible. Just keep in mind our country, which is a small country compared to the whole world, needs 2 terawatt-hours every day for the industry, and therefore that means we have to make more electricity, and which is left over will go into chemistry, make chemical compounds with higher value. Why should we focus on that? It's the good stuff about electrochemistry. It's inherently safe. That means the reaction is close to the electrode or on the electrode. This means as soon you switch off the electricity, the reaction will cease. Therefore, no terminal runaway reactions are feasible. This is extremely safe. Then we can avoid to have some noble metals or rare element critical resources. Since you bring in one side the electrons, you take it out on the other side, you have virtually no reagent waste, and this makes it extremely green. And of course, the most important part for companies now is you have new synthetic approaches you can make a shortcut of many steps and create IP space. The Americans call this disruptive technology or game changer, and I'm absolutely convinced this is the case. We usually have a similar container like the organic chemists like or love their round bottom flask. We just have a 2 electrode arrangement. This is a very simple arrangement, but this does usually the job. And the question is, how much does it cost for molar conversion? That means we have 2 electrons for 1 bond formation, and then this corresponds in dollar or in euros. It's more or less the same, but you see, most reagents are much more expensive. Therefore, this is really a technique we need for the future, and this translates to the amount of energy per kilogram, which is of course dependent on the size of the molecule you make. The important part is you make some anions, which could be very basic, on the other side, some cations, which could be very acidic. Oxidation reduction is almost trivial what you can do, but you can exploit the radical nature of the species you generate, or the basic nature of that. Since we are synthetic organic chemists, that means we are interested, of course, also on the current voltage curve, but it's not a driving force. The important thing is we want to accumulate a product. That means you have to look on the reversibility of the reaction, or you have to design it in a way that you can accumulate. It's not eaten up by the counter electrode or by the same electrode on a different time scale. Usually there are only 3 ways to operate an electrode. One of them are inert electrode materials. You just make the electron transfer. This is often not possible because the system of the molecule is not responding to the oxidation potential. Then you need a catalyst on the surface that we call this as an active electrode, or you have regenerate a system. If you make it on large scale in the batch type, this is still okay. For flow cells, this might be a little bit more difficult or challenging. Keep in mind, we have a lot of parameters if you do the electrosynthesis. It's not everything happening on the electrode. That means at the very beginning, you have the electron transfer. This is the initial step. This is the ticket to the party. If you don't make it to the party, there will be no fun, but you can screw up on the party, then you don't come to the final end. Therefore, both parts are very important, and there are many parameters which are involved. Here, the electrode material, the potential, the over potential. On the other side, the solvation is very important. There's some numbers which join both sceneries, like the current density, and therefore, since you have a lot of parameters, the best way for the beginning is screening. This is stuff you usually do. There several devices out there or described already for a longer time. You can use even more modern techniques like design of experiment, or even the more advanced ones, which are machine learning. But this requires a system which provides you relatively accurate data. And this is the device we use. If you look at that, we start with that, and after screening, you want to make larger amount of material, and then you need an electrolytic cell which is feasible, that you can do several grams of compound. And today we talk about this area. If you're successful here, of course you can go to larger systems, for example this kind of stack cells, but then you're already in the range which goes to kilograms. Okay, that means what we're talking today is that's the backbone for electrosynthesis, is the screening, and then you're not going to flow, which is a little bit more tricky. You go directly for a batch type cell, and this gives you sufficient amount. If you want to use that as an intermediate for more complex synthesis, this is usually the way to go, and it's quite simple to do that. This is important because if you look at an electrochemistry book, then you will see a lot of numbers. For example, if you look at the important thing is for molecules like an electrophore. If you look at that, then you will see you have here different areas which could be oxidized, and the one which is most easy oxidized will be oxidized. There's no way out. And in the CV, you're not operating here, you're somewhere operating here. That means anyway, if you do a 2 electrode arrangement, there will be, if you have depletion at the very end of the electrolysis, of course, the potential will increase. But then this means already more than 90% is converted. Therefore, almost quantitative conversion is possible. And therefore, you can do the dial-in reactivity by potential control. If you add a redox reagent, and this makes it also very, very selective. I refer to this paper here, which a lot of myths which are often narrated or translated to electrochemistry can be avoided, and it's quite simple to fix that. The most easy way to work with is the so-called undivided cell galvanostatic mode. That means you have a simple electronic periphery, and it's not only that you need a fancy glass blower, or it's already available. You can buy some plugs and some glassware, and even the holders and the electrodes. We put that together also with how to purify or to clean this kind of electrodes. It depends on the electrode material. There's no general way. Sometimes you have to rinse it off. Sometimes you have to flame anneal it. On the other side, you can mechanically go on that, but it's quite different which kind of electrode you have. These are the glass vessels. It looks a little bit more fancy in that way because it's a typical beaker one. It's a relatively large plug, but here you can work close to the boiling point. Therefore, we have it joined on the side. But it's the important thing is that you can use these plugs as well, not only for a glass system, as I have shown you. You can just use the same plug on a larger beaker system. And the important thing is that you can have a simple electrode dimension which can be directly attached to that. Just to show you the variety of the electrodes you have is sometimes you have thin metals. That means if you have some noble metals like often platinum foil or even maybe silver foil, then you have this kind of Teflon dummy. You wrap it around that, and it's just a metal system, and you can put it into that and screw it to that. If you have a solid electrode material like stainless steel, then you can just use it and put it there and fix it by the screw. This is quite easy to do. If you have a little bit more foamy stuff, then you need the holder, and you just put the screws through the foam, which gives you a good contact like nickel foam. There's some electrodes out there which are sensitive surfaces. The surfaces are quite stable, but mechanically less stable. For example, bond-up diamond, which is on a support of silicon, and then you have the one that you have a kind of a metal lid which goes on the surface, and this gives you sufficient conductivity that you can easily do the electrosynthesis. And this does not harm your electrode. Therefore, this keeps it in a good intact way. The important thing is that you have to mount them, and if you mount them, the coplanar arrangement is often very important. If you don't have too much supporting electrolyte, then by the Kohl-Rausch equation, the arrangement is very important that you have homogeneous field. Then you arrange that with the chemicals, you immerse that, and the next step is that you can contact this to the power source, and then you get started. The only important thing is that if you make a 2-electrode arrangement, either you have a column counter, or you just have a clock and a stop clock, and then you stop it at a certain time. You can calculate that by the electric current and by the time, and then you have to stop it, otherwise side reactions will start afterwards. Some words about the electrode materials, and many people think that carbon is carbon, it's the same element. We put here some stuff together, and then you see different brands of graphite make it different. What kind of, if you different anodes, how good the yield is. Sometimes it can be extremely explicit. If you look at that and you see Sigrafina Duracell, this is much better than on this. If you have this system here, this carbon system. The reason of that is that carbon consists of sp3 and sp2 carbon, and even the mixture of it could be crucial and important that the reaction works. Therefore, it makes sense to test different carbon versions. Some words about the electrolyte. The electrolyte is something what we call everything between the electrodes. That means solvent and supporting electrolyte, and basically it's also with the substrate. The ion conductivity, if you use large amount of salt, as you see, after a while, you have increasing conductivity by the concentration, and then it's not anymore beneficial. The reason for that is the ion pairing. Therefore, that's one point, is the conductivity. The other point is, just keep in mind, think about if you have anions and you want to do an oxidation, they will compete at the anode with the organic substrate. And the organic substrate is in most cases not charged. That means the organic substrate doesn't come too close to the electrode. Therefore, usually we work with lower concentration of supporting electrolyte, usually below 0.5 molar, in most cases even 0.1 molar concentrations. Just to give you a clue what you can do a co-electrolysis with arenes and phenols, or with phenols and phenols, and then you see you make a cross coupling without leaving groups, and you have a really exclusive selectivity that you get the biaryls here. And this was done in larger cells. I will show you some of them that you can make directly gram scale and even multi-gram scale with a workup. Even with this one here, this example we have here worked even better. With one side is protected with a silyl group. The reason why this works better is it's more twisted, therefore you do not generate a larger pi system. And on the other side, it's very important, the solvent is stabilizing the final product, and this is even after crystallization, you have 92% isolated yield. And I think this is, even on gram scale, really something which is really interesting. Even with things like aniline, if you oxidize them, you get polyaniline. That's the black stuff of your pans of the genes, black genes. And but if you use that with protective groups on the anilines, then you can use also the solvent mixture H-methanol, and you get even these compounds in very selective way, and you can escape the evil darkness of the polyaniline. This is a playground, and most of these reactions were done in multi-gram scale in a simple 2-electrode arrangement. Just to show you, even for natural products, we did this kind of compounds here. These are some morphines, and we did this at the very beginning with a platinum anode in a batch type. And then if you optimize that, you see that this kind of stuff, and we worked at this specific temperature, and you see a bonded diamond anode and a platinum foil cathode went to almost 70% isolated yield, and in flow we did not reach that. You see, even in batch you can get really good results which can be used even for more sophisticated molecules. And the molecules we used were that this is coupled, and this is selectively coupled between the 2' and the 4A position, and then you get this central intermediate with 69%, and then you do the typical organic transformations you need to make this molecule, the oxycodone, which is has not a good reputation, especially in the US at the moment. Just to give you a clue, it's a very broad application. You can do the electrolysis within these cells simply with sulfides and cyanamide. You get the sulfonylamines, and these are once more oxidized indirectly electrochemically with the periodate, and then you get this sulfoxaflor, or you have the medical relevant intermediate here as well. You see, this is something you can easily use, and you can use this with larger cells. I give you an example here, which was done recently with a colleague in Switzerland. It's an electrochemical shuttle, and the electrochemical shuttle you see here, it's usually transfer of 2 groups from one double bond to another double bond, and then to generate the double bond here. And if you want to do this with 2 halogens, it's very, very difficult, but it would be very, very interesting, because then you can replace chlorine and bromine as reagents. And if you have to buy bromine and store this in laboratory, then you see it's very corrosive. Transport is challenging, and therefore it's quite expensive. It would be much easier if you could use some of these molecules. The problem is that the nature, if you do this by catalysis, metal catalysis, then you have the problem that better H elimination is one of the big problems. And then you generate all the time the vinyl X version, and you do not replace both groups. And it's so favored that you cannot do this one here. And therefore, with a colleague of Bill Morandi from ATH Zurich, we developed this system that you have the bond cleavage here, which is done cathodically, and then you get the double bond system. You have the two halogenides. These were anodically oxidized. Sometimes you need a catalyst here, and then you generate this one here. We have both electrodes were used, and that's the reason why we have both electrodes in one of these cells. You can use them. I don't want to go into detail here, but the important thing is you can do this on larger amount here in multi-gram scale. You do this. This is a bigger beaker. You just have the same plug, and you need some joints in between that you get of a larger system. But it's very simple setup, and you can use that. It's also for the chlorine. You can use that. There's only one thing I really want to stress here. It's not about the different scope, which is really brilliant here, but the important thing is that you can convert something which is a really nasty compound. When the people made it from the 50s to up to the 70s, lindane, they made about 80% of waste. And this was just deposited several million tons in the soil, and just covered, and they try to forget it, but it's still there, and it's toxic. But what you can use by electrochemistry, you can make benzene of it and transfer the chlorines to a useful product. And this is, I think, something which is very important. Here you see the same of these plugs. Now we have a different container, since we have to heat that, but you can use that in a very simple way to combine the electricity with your other organic reactions. And that's was what I want to tell you. And I'm open to questions. Please, fire.
Okay, well, Siggy, thank you. That was a fantastic little run through of some of the stuff you've been working on, and a very kind of whistle-stop tour of some electrochemistry. We've got some really good questions coming in. So I'm going to start with a question from Sri Krishna, which is, he's asked a couple of questions really around the shape of the electrodes, and does that make a lot of difference? How do you choose what shape of electrode might be better? Do you use different shapes for different applications, that kind of thing?
Usually we use coplanar arrangements. Just keep in mind, if you make an angular arrangement, then only the tips have the closest field to each other. And if you have rods and you have on planar ones, the rods have a different profile of electric field on the surface, and therefore often a different outcome. Sometimes you can use that if you want to have on the counter electrode a very small surface, then you can use a thin rod. This is one example, but if you exploit both parts in an equal way, this coplanar arrangement is very useful.
Okay, that's a great answer. And we've got another question from Mikhail, who asks, he says, it might be a silly question, but there are no silly questions in my experience in these kind of things. Why do you always use a DC current? Is there would there be any situation where you might use an alternating current? Presumably that kind of depends on whether there's any difference in the two electrode materials, or
there are some recent papers by Hild and Barron and other people where they use AC current. The reason why we use DC current is we want to have a certain efficiency, electric efficiency. If you use AC current, you make a polar, you make the reversal, and then you have the surface have to be restored as well, and this usually swells a lot of energy and therefore it's so capacitive current which you invest. I think they have spectacular results, but the problem is that you will get by AC different reactivity, but the energy efficiency and the corrosion at the electrode, the effects are tremendously high. And therefore, I think for production, this will be not yet on a ripe situation, let's call it like this.
Okay. And I guess looking forward, if you were thinking about a factory and if you're thinking about powering it with renewable energy, things like solar and wind power often, or certainly solar would be putting out DC, so you wouldn't have to mess about with inverters and that kind of thing.
It's if you talk about later on about energy efficiency, therefore keep in mind you have to pay not only the current but also the voltage, and therefore every transformation from DC to AC you lose some part of energy. Yeah.
Great. Okay, so we have some more questions. We've got loads of questions coming in. These are really good. So one from Vijay Monahan. When do you consider using different kinds of cells? So you've mentioned 2-compartment cells or a beaker cell or 3-compartment cells. How do you choose which type of cell to use in a given reaction?
If you have the problem that you cannot interrupt the reversibility, then you need a 2-compartment cell. But there's still a possibility for the poor guys, like academic people. That means you have a big cell where you make the big electrode, where you make the working stuff, and you use a small counter electrode. It's the so-called quasi-divided cell. It was invented in the 70s by industry laboratory, and then the hell is going on around the very thin counter electrode, but you lose maybe 5% of your product, but this usually works. And this is one simple approach which can be used as well if you have not a cell with a divided cell or something like this.
Great. Yeah, I guess there's quite a few different parameters to take into account into that decision, but yeah, fantastic. Yeah. Okay, so next question is from Yilin. She says that looking at a lot of your reactions that you've put up on the slides are run at 50 degrees C. How does the temperature as a parameter change? How do you arrive at what kind of temperature to use, and how does that affect the reactions?
Important thing is you have the conversion at the electrode. The temperature is not that important, but the problem where temperature is very, very important is you need to transport from the bulk to the electrode and from the electrode back to the bulk. And the only thing what you can do is by enhancing the temperature. Of course, the molecules have to be stable and immediate, but also keep in mind, if you elevate the temperature, the conductivity is much higher. That's the reason why most technical electrosyntheses are done at elevated temperatures. Electroorganic synthesis at 80 degrees, and some of them, like Roran production, close to 90 degrees.
Okay, that's a great answer. Thanks very much. Okay, so the next question we have is from Jean, and he says, is it possible to scale up electrosynthesis under potentiostatic conditions?
Clear answer, no. People try to do that. One big company in Germany, BASF, tested that, and it's not necessary because if you can control the current quite well, the stuff which is first oxidized will be reaches the electrode. If you go too high with the current, then of course it will be unselective, but in a certain corridor, you're absolutely safe.
Okay, that's great. And that comment about selectivity kind of leads on to the next question, which is from Friedrich. And he's saying, how predictable are the regioselectivities in this transformation when you've got different potential sites of activity? Is there any way of predicting it, or does that come into the screening, or?
Predicting is sometimes difficult because you can say which part of the molecule will react, and if you have regioisomers, it could be different if you use different solvents, different electrode materials, and even different currents. That means here it seems to be that if you use, for example, high current density, then you have maybe no selectivity. If you have low current density, the selectivity is much higher. And the important thing is here it seems to be that if you have a alternating current at a certain frequency, you shift the selectivity. But this is a very, very new field, and it's poorly understood. I think that there's no clue at the moment. The people just collect some initial data at the moment, different groups, but I think that there will be some handles, but it will be not only the potential, it will be some more. It's about maybe the kinetics which is involved here.
Yeah, I guess with those kind of multifactorial problems with lots of different factors affecting it, that's where something like the design of experiments or the machine learning aspect comes in, when you really want to get a handle on that selectivity.
Absolutely. Yeah.
Yeah, great. Okay, so we've got a couple of questions here. One from Girish here. Solvent obviously plays a big role in the electron transfer process. Can what are the effects of using different solvents or blends of solvents to change the reactivity of the yield? And just to add into that, I guess, which is also solvent related, another question from Mikhail was about how critical is stirring the reaction? Does that make a difference?
Let's come to the second part of the question from Mikhail. Stirring, of the reaction is, you would anticipate it's very important for the mass transport, but keep in mind that the last micron in front of the electrode is almost not affected by stirring, even if you have a very strong stirring, because you have salts in there and they just glue a little bit. The closer you come to the electrode, it becomes more and more sticky, a swamp, let's call it like this. And therefore, that's one point. You can affect this strongly if you lower the supporting electrolyte concentration, and of course the solvent plays a tremendous role. Sometimes the mixtures are very important. We had this in the past that we used the fluorinated alcohols, and adding some water or methanol make a complete different reactivity out of it, because by solvation, some of the species become more reactive than the other ones. Therefore, solvation is an extremely important thing, which is almost ignored for a long time by electrosynthesis guys.
Yeah, fascinating. Absolutely.
And there's almost no theoretical treatment. Therefore, it's I would not say it's a white spot on the landscape, but it's almost unexplored.
Well, it's opportunity there for someone in the audience, possibly.
Of course. There are many young people, bright ideas. Yep.
Excellent. Okay. So an interesting question from Hussein. We've seen from your presentation and from the wider kind of literature, there's a lot of stuff going on in electrosynthesis at the moment. Now, can you give us an idea of how strongly this is being taken up in industry, for example, pharmaceuticals, chemical industry, where they're at with these things? Because you mentioned you're at DSM this morning, and
yeah. I can say without any problems, it's taken up by industry very seriously, because it will be the prime energy for the future. And if you can avoid to have critical elements like platinum, iridium, or something like this, this is of course the way to go. And for pharmaceutical companies, it's not the cost driving ones. You get new reactivity, that's one point. The second point is you can work metal free, and this gives you a complete different profile of contaminations. And this is extremely interesting. And then you can make large different molecules which have not been there before. I think almost every pharmaceutical company is working with that. And with the availability of the electrosyn, which was developed or co-developed by Phil Barron, it's plug and play now for them. I think it's at the moment a certain hype, but it will stay there. It will be not only just a wave. It will be accepted. It's a method. Compared to photochemistry, electrochemistry is easily scalable, and scalable on large range. That means the biggest factory at the moment which is working is about 40,000 tons at BASF with electroorganic synthesis, and there was by the Basel process before something with 300,000 tons. And as soon electricity is surplus stuff, they will reactivate many of these things, of course.
Yeah, so I guess that kind of comes down to, how that, I mean, maybe, so Hussein, who asked the question, sort of implied that he wasn't really seeing it in the pharmaceutical companies. But I guess if we're talking about production, then it takes a little while for things to kind of filter up. You know, the
Yeah,
drugs that are on the market now have established processes, but it's more likely, I guess, that we'll see it in newer things coming out where where they're developing the processes and this is becoming an option.
I think that's the point. If you have a process and you have the drug on the market, then you have the FDA approval of the process, and they won't switch it so easily. The point which is very important is, if you go to generic market, then you directly try to make it as efficient, as cost efficient as possible, and then it plays a role. That's one point. And on the other point, some really new drugs like the finerenone by a bio company, they have the wrong enantiomer of the final drug, is then oxidized because it's a hunch ester. It is oxidized, then and then you make once more from the wrong enantiomer by reduction the racemate, and this is then exploited. And since this is a 7-step synthesis, which is quite costly, this is simply a green step to use that once more. I think that's the point. You have to look where it's a benefit for the company, and if there's a clear benefit, it's not that it's a little bit better, it has to be a clear benefit, and then it's easily accepted.
Yep, that's fantastic. Okay, so we had some a couple of other questions. One which I think are related. So from Vijay Manahanan, Vijaya Mohanan and someone a bit lower down. Looking at sort of how do you know when to stop these electrosynthesis reactions? I think in one of your early slides you had a curve that, and you were marking it off at about 56 millivolts. Is that? Can you explain what that was? Because I think you kind of went over that fairly quickly.
Okay.
Can you explain what's happening in that?
If you do at the very beginning some screening, then you also test how much electricity you need to get a certain amount of your compound, and then you figure out you need 4 electrons per molecule, for example, and then you should design the reaction in your beaker that is stop it if you have 4 electrons for each molecule in there, and you notice by the current, and then you integrate it over the time. And some systems, like the most devices, you can control by USB port, or you need a stop clock to do that. This is the only way. And if you have the calculated one, usually you lose a little bit, but it gives you usually a good conversion. Just keep in mind the last 5% are not so easily converted, because then you have among all the other molecules within there only some substrate molecules, and they do not come in time to the electrode. But usually, as a synthetic organic chemist with 95%, you're quite happy.
Yep, absolutely. Okay. We've had a question from Lewis, which is around combining electrochemistry or electrosynthesis with ultrasonics. So would there be an enhancement of selectivity if the cell were to be immersed in an ultrasonic bath?
Indeed, there are some people who do that, like the atomic group in Yokohama, and we also played a little bit around with that. Keep in mind, if you have an electrode, which is a composite of several materials, ultrasonic treatment can destruct this electrode. The idea behind is that you use the ultrasonic treatment, that the stuff comes off the electrode, that you have a better mixing for the mass transport. Unfortunately, this could be also enhanced the corrosion. There's no general rule. Just if you have a layer of catalyst on the surface, this will be not a good option. But if you have a massive electrode like a stainless steel or graphite, you can use it. But graphite is also a little bit, depends on the type of graphite. It could be that the ultrasonic bath just grinds it, and then you have a black mud in there. Keep that in mind. test it, and if you see that something is falling off, stop it. Okay.
Okay, great. So just coming back to something that you mentioned there, you mentioned in your presentation that not all kind of carbon graphite electrodes are created equal. Can you give us a little bit more information about that, about the kind of differences you see between different types of graphite or carbon?
Keep in mind when the graphite is made, or the industry prepares that, then you have some graphite flakes which are pressed together, and between these flakes you have some pores, and if you do not fill up these pores, then the graphite will be easily disintegrate because of gas bubbles and other things. What they do is that you have a polymer which is soaked into the pores, and then it's carbonized, and then that means the sp2 from the graphite, and adjacent to that you have sp3, and therefore the graphites you can buy have different ratios of sp2 and sp3 carbon, and these have fundamentally different properties or features in electrochemistry. And it could be that you have a high sp3 rich graphite material. This behaves a little bit like diamond. And in addition to that, because graphite is usually, natural graphite is not abundantly available, they use carbon material which comes out from the petrol refinery stuff at the very end, and which is used, and that means you have often also some ashes in there, some metal traces. Therefore, some graphite could be not metal free. If you use it for pharmaceutical applications, you need a provider which says, okay, there is maybe some potassium in there or something like this, but absolutely no, or they know that's a little bit of manganese, a little bit of iron is there, but nothing else which could be toxic.
Yeah, and I guess it's very just not necessarily a problem, but just knowing exactly what's in there. So having the suppliers that can give you that information.
I really try to as a reviewer give the argument, please add to the supporting information the source of your graphite and the type of graphite, because usually the just right graphite was used, and this is difficult if other people, we know so much because we're standing on the shoulders of the old chemists which made tremendous impact, and therefore that other people can reproduce that. It's important that you write down which kind of graphite you use.
Yeah. Okay, so we have another question from Yilin, who asks, so you were talking about some halogenation reactions towards the end of the presentation, and I think some of them were taking the halogens from a pesticide molecule, hexachloro cyclohexane. Is there an advantage to using an organic source of halogen, or how does that compare with using halide salts? So if you were just, I guess in that example you were looking at trying to degrade a toxic molecule, right? But if you were just looking to introduce a halogen into a product molecule, would you look at an organic or an inorganic source of?
If you want to do it most cost efficient, then you would use rock salt, of course. It's definitely the one which is the cheapest source, definitely. And what I have shown was that it is a waste from the time in the 50s to the 70s, where the wrong isomers were just as a pollutant deposit in the landscape, more or less, and therefore it's there are two things what you can do with that stuff, or maybe three things. One thing is just ignore it and forget it and hope that the groundwater will not reach you contaminated, which is not a good idea. And the second one is to burn it. If you incinerate that, you need a lot of other fuel, because this is a flame retardant. That means if you want to burn that, you need about 20 to 30 equivalents of carbon equivalents to incinerate that at high temperature, because you have also to avoid some dioxins. And this is just an alternative to upcycle these pollutants.
Yeah, I mean, I know we've had stories in Chemistry World talking about sort of landfills in North Macedonia that are full of this stuff, and it's an absolute nightmare to clean up. But
Yeah,
okay,
it's 4
uh,
million tons in Europe, and we don't know how much is in China and India. There's no list for that, but I guess there will be also something. Yeah.
yeah, yeah. So if we can turn it into something useful, so much the better. Okay, so we've got a question from Ter, who is asking more about using electrochemistry to synthesize biomolecules like amino acids and other biomolecules.
Yeah, indeed it's used. It depends a little bit what you consider as biomolecules. They're precursors for amino acids for animal feed, which are made electrochemically as well, and but they're to make, for example, a good peptide formation electrochemically, it's not yet there. You can make some precursors, but to make a polypeptide wholly electrochemically, it's not yet established. But I'm sure somebody will come along with a clever trick.
Yeah, yeah. Just because we can't do it now doesn't mean it won't happen in the future. Excellent. Okay,
That's the
so
point. Just some doors are opened, and I am sure that I see so many young people who have clever ideas, and don't let you tell from other old people everything is known. Don't try this, okay?
yeah, absolutely. Okay, so I know. So we have a question from Javier. And I know that the focus of this webinar is mostly on batch type reactors, but you did mention the possibility of continuous flow reactions early on in the presentation. Have you done any reactions where you've done the same reaction in both batch and continuous mode? And can you kind of compare and contrast what are the advantages, disadvantages of the two different modes?
It's I have shown one example for the oxycodone synthesis where we did it also in flow, but we have several examples where we did this. And in many cases, the yield goes even up by flow. And but the optimization in flow is a little bit more difficult. Keep in mind, you have two electrodes, and then you have to pump through it, and then the current density is there. Then you have um, uh, the flow rate, and the other thing is, of course, the spacer is there, and all of this stuff is highly dependent from each other. That you see that in the design of experiment, then you have a three-component interaction and things like that, which is very uncommon, and this makes it highly so sophisticated. That means, under the line, the optimization flow needs a little bit more efforts than in batch. But if you do that, it could be that the yield could be even higher. In the oxycodone synthesis was not the case, but we have several examples where the yield could be even higher in flow.
Yeah, and just as an extension of that, I mean, you mentioned earlier talking about all of the different factors that you need to optimize that you might do in a batch process. Does that optimization data kind of transfer over? So if you try different solvents in batch and different conditions in the batch reactors, does that transfer over to flow, or are you starting again pretty much from scratch?
No. If you have this in batch, it's in a splendid starting point. Usually you have to do the adaptation to flow, and this, if it works in batch, then you have a fine tuning you have to do. But this fine tuning can go, if you start in batch and you do the initial flow, then you maybe erode from 60% yield to 20, but then by fine tuning you can go up maybe to 80. Therefore, at least it works directly, and then you just have to figure out the right properties, the right parameters set, and then it works. But
Great.
to start by scratch with inflow, it could be very, very difficult for a new reaction.
Yeah. Okay, so we've got one more question from Hussein, who's asking about refreshing carbon electrodes. I mean, I know towards the start of the presentation, you were talking about different ways of doing it, and that kind of depends on the structure and material of the electrode. But so he's asking about refreshing carbon electrodes in the difference, any differences between industrial scale or academic scale, or if you have high absorption of material onto the electrode, what's the best way of getting it off? I guess partly
it
depends
depends.
on.
Yep, and then onto the material, and even the large facility at BASF where they have do the Lismaral synthesis in large quantities, the carbon electrodes have to be, graphite electrodes have to mechanically cleaned, and that's something which is inherently the bad stuff about the cheapest carbon electrode graphite, that also some organic radicals can click on the surface. Classic carbon is a little bit more stable towards that, and usually if it is mirror type shiny, you don't have to clean it, just rinse it. And bond-up diamond is very easy to clean. You just immerse that in sulfuric acid, diluted sulfuric acid, as an anode, for example, and then you just burn off all by oxyl radicals which are formed, hydroxyl radicals, all organic stuff which is on the surface. These are the different ways, but graphite is usually only mechanically cleaned.
Yeah, that's, I mean, yeah, I guess it's a difficult question to answer specifically, but there's there's presumably about as many ways of cleaning electrodes as there are electrode designs. So you know, working out what's right for your particular combination is going to be important. That process. Let's have a look.
Maybe also very important, a quick version. If you have a graphite electrode and you get it from your colleague and it's maybe a more porous graphite, it could be some molecules inside from the reaction of your colleague, which makes maybe the first trial a little bit difficult because you find molecules you never anticipate. Keep that in mind. Therefore, taking off some microns by sandpaper of the graphite electrode avoids that, just as a hint.
Yeah, okay. So there's a slightly related question to that from Norsang. Is there something that you can do if your product forms a precipitate that then clogs or blocks up the apparatus in some way? Does that have any negative effects on, or are there any ways of avoiding negative effects from that kind of thing on the reactions?
If your product precipitates, then you are often quite lucky because that means the counter or the reversibility on the other electrode is not an issue anymore. Keep in mind, if the solubility drops of your product also by the Nernst equation, it becomes much more stable. Therefore, there will be not much overreaction or something else. The problem could be that on the electrode, some crystals are growing and then it covers the electrode. There's one thing what to do, either mechanically remove, or if you have the same electrodes as cathode as anode, then after 10 minutes, you make a reversal of the electrodes. And this is more often something which works. Then you do not lose too much energy because of the polarity switching, but it helps then that the crystals pop off. Just keep in mind, sometimes you make an oxidative coupling and the hydrogen evolution is the counter reaction. And if you have to remove the crystals, then usually the evolution of hydrogen just lifts off the deposit or something like this.
Brilliant.
But it's not so bad. Often it's quite good.
Yeah, okay, thanks, Siggy. Okay, so this is going to be the last question. I think you've done a fantastic job of answering some of these questions today, Siggy. So the last one, which is a fairly topical one, is from Lewis. He's asking about whether you think it's possible to destroy PFAS, so the perfluoroalkylated substances, using electrochemistry. It's something that we're seeing quite a lot in the chemistry news at the moment, about the persistence and pollution of these kind of compounds. So do you think electrochemistry has a role to play in cleaning that up?
Yeah, electrochemistry can even knock down Teflon. You keep that in mind. Everybody who is organic chemist knows that if you make a birch reduction, you have these stirring bars, which are glass covered version, and this is the real problem, because you go to a regime which is minus 2.5 volts or something like this, and then the carbon fluorine bond is unstable, very unstable, and then you reduce that, the fluoride pops off, and then you can do something else. Defluorination is possible by electrochemistry, and therefore I think it will be the key to do that. Of course, you can do this even with lanthanides or something like this, but keep in mind several lanthanides are quite expensive, toxic, and some of them are even radioactive, or have some isotopes which are radioactive. Therefore, it would be not the greenest choice to do that. Therefore, it's worth to think about electrochemistry, of course, yes.
Brilliant. Okay, well, as I say, thanks, See, that you've done a bit of a marathon job there of answering quite a lot of questions. So thanks very much for that. It's absolutely fascinating topic. Thanks again to Merck KGaA for sponsoring this webinar. There's been a few, I don't know if there's a few addresses there that have popped up on the slides where people can find out some more information if they want to. Those will obviously be included in the recording that you'll get a copy of in the next few days. Again, if you need a certificate of attendance for any reason, even if it's just for your own records, then that will come along with the same email in the next few days as well. If you liked this webinar, then do remember to check out www.chemistryworld.com/webinars to see what other topics we've got coming up. We've got another one with Merck KGaA in a couple of weeks' time, so do go and have a look at that one. And we hope to see you again in another webinar soon. So I'm Philip Broadwith. I'm the business editor of Chemistry World, and we will see you again soon.
Okay, was my pleasure.
Thanks very much. Goodbye.
Bye.